Okay, welcome back. So now we're ready to do some turtle math. Right, volumes by shells. Actually, this actually doesn't have anything to do with turtles, of course. But we're going to be using what are called cylindrical shells. The image you want to have in your mind would be if you've ever seen old either concrete or terracotta pipes, kind of like this picture right here with these pipes here, where you have a pipe and you have an inside part that's completely empty, and then you have this little shell. This is what we want to think about when we're dealing with cylindrical shells. It's another way to find the volume of a solid. Okay, so you're kind of looking at this idea here is you have these pipes. I'm going to try to draw a picture later on. It's not going to look nearly as good as the picture of one of these little pipes. But this is the idea that I'm trying to get at here with these cylindrical shells. It's this like pipe type picture. That's what we're going to get to. Because if we come back to this problem here, I have this graph. My function's y equals f of x. All right, y is a function of x. And let's say we wanted to take this region here, right, this region inside the graph, and instead of revolving it about the x, like we did before, what if we wanted to take this region and we wanted to revolve it about the y-axis? We wanted to revolve it about the y-axis to generate a solid. So we want to revolve that about the y-axis. Well, then our approach that we've used with washers and discs would require us to take this shape here. And the problem is, as a function of y, we'd actually have to look at the two parts of the actual graph itself. Now this is a quadratic, so we could do that. We could do that problem. I could take this graph and think of my two wings here as two separate functions, and then find the volume by using my washer formula. But what if it's something more complicated? What if it's something else where this just isn't practical? This approach just isn't practical. So instead, we once again subdivide. So looking inside here at, say, the interval, the ith interval, so xi minus 1 here to xi. Right? So what I'm going to do is I'm going to look at this rectangle, the one that runs not perpendicular to the y-axis like we did with washers, but parallel to the y-axis. I'm going to take this thing and I'm going to take that shape, that rectangle, and I'm going to be revolving that about the y-axis. About the y-axis. And what I want you to realize is that when I do that, then I've actually created one of these pipes. I've actually created one of these terracotta pipes, okay, or what we call a cylindrical shell. Okay, that's what we're actually going to generate when we take that thing and revolve it. Is you're going to have the inner part of your pipe and then the outer part. And the actual volume that we're worried about is the volume of that clay that's happening in the pipe here. That's what we're actually going to be looking at. So when we do this, we're going to generate a shape that looks like this. And again, apologies, my drawings aren't always the best looking. but basically we're going to have an outer pipe, an inner pipe, and an outer pipe. And we're going to be generating a cylindrical shell like this. And it's going to have, that hole in it all the way down through. Now, what do we have here as far as our labeling system? In this situation, the height, the f of x function, is actually giving me the height of this cylinder. So that's my f of x function. The inner radius is not a function value, but rather the inner radius here is the inner x value here. In this case, xi minus 1. The outer radius is your second x value, xi. The thickness of my little pipe here, this little piece right here, is the width of that interval, delta xi. Now, mathematically, we have shapes that we can do a whole lot of stuff with that we couldn't do with our terracotta pipes, at least without breaking them. So imagine if we took one of these pipes and we sliced it down the length. So we sliced down the length of the pipe. Okay, and then imagine further that this wasn't made of terracotta, that it was made of some very much more malleable substance that we can actually roll it out. Okay, then what we'll actually have is the same thing that happens if you ever took a can of soup. Cut the top off, cut the bottom off, sliced it down and rolled it out, is you're going to have a flat piece of metal that's actually almost a rectangular solid, almost a rectangular prism. It's not quite that, but it's pretty darn close. So when we roll this out, we're going to get a shape that looks something like this. Something like this. So let me draw a picture here for you. Get my pen back. So I'm going to have one rectangle here, and then I'm going to have a second rectangle, say here, and then just connect my edges here. So I'm going to have a rectangular solid, almost. It's not quite a rectangle because of something I'll mention in a moment. But the height of this object is just going to be f of x. Same height that it was over there. So that's just f of x, actually should be f of xi. The thickness of this is my delta xi. The length will actually be the circumference, or the one side, the circumference of the outer layer, and then the other length back here will be the circumference of the inner layer. And those will be slightly different because they have slightly different radiuses. But we're just going to approximate it. I'm only going to worry about the front end and realize that it would be the circumference. Circumference, remember, is 2 pi r, 2 pi times the radius. So this would be 2 pi times xi. The other side, again, will not be exactly the same length. That's why I say this is almost a rectangular solid. It's not quite. But that's okay, because this is a good approximation. This is a good approximation. And when we take the limit later on that allows the width of our subintervals to go to 0, then it won't be an issue. This won't be an issue. And so the volume here of this thing, if we treat it as a rectangular solid, the ith volume would be approximately the area of that pseudo-rectangle, or the volume of that pseudo-rectangle, which would be f of xi times 2 pi xi times delta xi. Again, this is not quite a rectangular solid, but it's pretty darn close. It's pretty darn close. Okay? It's pretty darn close. And so when we take the limit and add all this stuff up, or add all this stuff up to get the air volume, and then take the limit, we turn it into an integral, and it turns out the volume is the integral from a to b of 2 pi x times f of x dx. 2 pi x times f of x dx. That's going to give us the volume of our solid using cylindrical shells. And if we were to continue on and have a region that was, once again, instead of touching the x-axis as it did here, if we had a volume that we were generating that was based off of a region between two functions, right? So two functions f and g, and we were looking at this region here, and we were once again revolving about the y, so that we're using cylindrical shells, then the height would just be the difference between f and g, and we would get this volume formula, integral from a to b of 2 pi x times f of x minus g of x. Notice the difference here from the disk. When we did it with the disk, we were actually squaring those. But here, in this problem, you're only dealing with the height of your cylinder, h. Whereas before we were doing the differences between the radiuses in the cylinder and the cylinder formula. It's 2 pi radius squared times height. So in the disk and washers, that's why it was f and g squared. But here in the shells method, it's just the difference between f and g, just the height. That's why they're not squared. Okay, so that's the setup. That's the introduction. Now we're going to pick up in some future videos on how we actually compute. Use these shells now to compute. And again, we have two versions of it. The one where the height function is touching the x-axis, and if it's a region between two things that we're revolving, then we use the difference of the two functions. Okay, and again, the key idea here is your shell is laying parallel to the axis that you're revolving about when we're doing shells. Whereas disk, you're revolving perpendicular. Your rectangle is perpendicular to the axis. And so that's the difference between the two methods. Sometimes you can do something with both methods. Sometimes that just doesn't work. Okay, so we're going to look at some examples in some upcoming videos, but I first wanted to get this introduction for how this formula comes about. And so now we're going to see how to use it.